In this video, I'm going to cover the Python data visualization library Seaborn. Now, before you get started with Seaborn, you're going to need to make sure that you're comfortable with the Python programming language itself and some of the other data science libraries. So you should be comfortable with the numeric Python library numpy and the Python and data analysis library pandas. You should also be comfortable with the matrix plotting library matplotlib. So Seaborn can be thought of as a library that bridges the pandas DataFrame structure to matplotlib. So Seaborn makes it easy to plot data from a data frame, and it simplifies the matplotlib code that is required in order to plot data from a data frame to create commonly used data visualizations that are used in data science. So I've already created a written guide which this tutorial video will roughly follow along with. So let's get started with some matplotlib revision first. So let's import numpy as np and import matplotlib.pyplot as plt. So we're going to create some x data and some y data. And the x data is just going to be linear space data, and the y data is going to be the sign of this x data. We're also going to have y data 2, which is going to be the cost of this x data. And now we're going to create a figure and axis using the plt.subplots method. And then we're going to create a line plot using the x data, the y data, and labeling it as y equals sine x. We've also set an x label, a y label, and a legend. And what we're going to do now is just append a second line to this list of lines. So now, if I add the command plt.closeAll, it will close all previous plots and then plot the new plot. So this is what this plot looks like. Now we're going to import pandas as PD and import Seaborn as SNS. So if we type in sns.setStyle, what we can do is set a style to all of our matplotlib plots and Seaborn plots. So if we set the style to white grid, notice that all the plots now have grid lines. If we set it to white, we get the white background with no grid line. We can also set it to dark grid, which sets it to dark with grid lines, or we can set it to dark, which sets it to the dark background without grid lines. I'm going to use white grid by default in the rest of this video. So now what I'm going to do instead of having a sine and a cost plot is I'm going to have a series of sine plots which each have a different amplitude. So we're going to create this empty list lines and we're going to append to it the plot of x data and y data. And we're going to apply an amplitude to the y data. And if we put this in a for loop, we're going to get a series of sine lines. So we can just modify the placement of the legend now. And then we can increase the line width to 3. So notice that Seaborn uses its default color palette, and all of these 10 lines are a different color. If we increase the number of lines that we're going to create, what will actually happen is that the color palette will start to repeat itself, i.e. it'll run out of colors in the color palette and then go back to the start and then use all the colors in order once again. So if we type in sns.colorPalette without any input arguments, we get this list of tuples. And each tuple has 3 normalized floats, which correspond to a red, green, and blue value. So let me just assign this to a variable colors, and we can view it in the variable explorer. So once again, we see that each item in the list is of the type tuple, and it's of the size 3. So here, if we go to our plot, we can see we went through these 10 colors. And then when we've reached the end of the list, we go back to the start. So the last 3 lines are the first 3 colors. So the default palette is called tab 10, and we've got this keyword input argument palette which defaults to tab 10. We can add the keyword input argument as CMap and change the value from false to true to view it as a color map. And Seaborn has a number of other inbuilt color palettes such as Pastel, which is essentially a washed out version of the default color palette, which creates the effect of a pastel, as the name suggests. So you can see the difference when we update the color palette using the Seaborn method set palette. There are other color palettes such as set 1, set 2 and set 3. And each of these color palettes has a different number of colors. So you'll see this before the colors begin to repeat. And there are also the circular color palettes such as HLS, which stands for Hue, Saturation and Lightness, and HUSL, which is a human-friendly saturation lightness. So in addition to the discrete color palettes that we've used above, we've also got sequential color palettes. And in this case, there's actually too many lines for the sequential color palette to make sense. If we lower the number of lines, we can see that this indicates that the amplitude is increasing as we go to the next value in the color palette. So we can also create a light palette by specifying a color and then specifying the number of colors. So the light palette will start from white and then go to the color you specify. The dark palette will start from black and then go to the color that you specify. And these can also be reversed by using the keyword input argument reverse and assigning it to the bool true. So let's assign one of these palettes to a variable and then assign this variable to the keyword input argument palette in the Seaborn set palette function. And we can also use the blend palette function to blend a list of colors together. So for example, if we go to Microsoft Office and we have a look at the standard colors, we can have a look at what the hex value is for each of these standard colors, and we can create a blend palette from it. So let me just type in the list of all these colors, and in this case we've got 10 colors. So we'll set n colors to 10 and we'll set this CMap to be true. And if we have a look at the CMap and compare it to the standard colors in Microsoft Office, we see that they're identical because the CMap is created from these standard colors. Okay, so let's now go to our plot and we'll create this palette standard colors. And then we'll use the Seaborn set palette function to set the palette to standard colors. Now, because there's only 10 colors added to the palette, once we exceed 10 colors, we end up repeating the starting colors of the palette. And if we set n colors to be more than the number of colors we provide, the Seaborn function blend colors is actually going to create some additional colors from the colors provided. Let's now have a look at the XKCD colors reference. So these are essentially names of colors. So you can think of these as the names of cans of paint, and each of these names has a color, which in the case of Seaborn recognizes it as a hex value. So if we have a look at the Seaborn reference xkcd_RGB, what we actually get when we assign it to a variable is a dictionary. And so the keys in the dictionary are the names of the colors, i.e. the names of the cans of paint, and the values are the actual colors themselves that are recognized by Seaborn or matplotlib in hex values. So for example, if we type in sns.xkcd_RGB and then use the key sky blue or hot pink, we're going to get the hex values for these colors. So now that we understand this, we can use the Seaborn xkcd palette function, and here we can assign a list of colors, and all of the colors that we are going to use must be keys that are within the xkcd RGB reference. So if we assign this palette to the variable name xkcd colors and then set the palette to this, we'll see that our plot now uses these colors. So there is also the Seaborn function MPL palette, which stands for matplotlib palette, and this will recognize all the palettes within matplotlib. So if you have a look at matplotlib choosing color maps, it's going to give you details about sequential color maps, and then it's going to give you details about diverging or qualitative color maps. And Seaborn itself is built using a number of modules, and one of the modules is palettes. So if we have a look at this module palettes and then have a look at what's in it, we essentially see all the functions that we've just used grouped together under this palettes module. Now you'll probably notice that there are a number of Seaborn functions related to color palettes that begin with choose, and these are for interactive Python notebooks, not Python script files. So in order to have a look at these, we're going to need to switch the IDE to JupyterLab. So let's go ahead and launch JupyterLab, and we're just going to copy and paste some of the code that we've previously used in Spyder. And here we're going to choose the diverging palette and set it to palette, and then use the Seaborn function set palette and assign the palette to this palette. So what you can see when we launch this cell is that we have an interactive menu to actually select the color palette, and then this will apply this to some later plot. So this plot created uses the selected color palette as expected. Okay, so that's an overview of setting the style and setting the palette. And what I'm going to do now is have a look at data in the format of a data frame. So let's create a data frame called linData. And we can create a data frame using a dictionary. So we've got key value pairs, and I'm going to have as the keys X data and Y data, and I'm going to use the numpy function arange to create a numpy array using a start of 0, a stop of 11, and going up in a step of 1. And for the Y data, I'm just going to add some random noise. And so the data frame is created as expected, with the keys being the names of the series and the values being the values in the series. Let's create another series called even and odd, and we essentially want even to be true when we have no remainder when dividing by 0. And for this to be false when we do have a remainder. So let's change the series type to category, and we can have a look at the D types of this data frame. So if we type in the data frame name followed by a dot, we can access a series as an attribute, and then we can access categories as an attribute, and then access one of the category methods here, such as rename categories. And in this case, we're going to supply a dictionary which has the old names as the keys and the new names as the values. So now these are named even and odd respectively. So we'll come back to this data frame later. What we're going to do now is have a look at the sign data that we created before, but this time we want it to be in a data frame. So let's create a data frame of x and y values. So the x values are going to be linearly spaced, and the y values are going to be calculated using the sign of these linear spaced values. So this data frame just has one of the lines that we've seen earlier. So what I'm going to do now is I'm going to create another series called amplitude, and I'm going to assign this to numpy 1s, and I'm going to have it be the same length as the other series. So this is still just one of these lines, but what we can do is we can use a for loop, and we can use the DataFrame method concat to concatenate new data to the original data frame. So the new data frame that's going to be concatenated to the original is going to have the same x values. The y values are going to be multiplied by the index in the for loop, and the amplitude is going to be multiplied by the index in the for loop. So this gives us the series of lines that we used before. And if we have a look at the index, we see now we've got multiple 0 values, multiple 1 values, and so on. So let's reset this index. And now we see we've got 1,000 different values in this data frame. So we can have a look at the data types, and in this case we see x, y, and amplitude are float64. We could change amplitude to category if we wanted, but in this case we're just going to leave it as float64. Now Seaborn includes a number of example datasets. So if we use the Seaborn function getDatasetNames, we get a list of strings which correspond to the names of each dataset. So for example, we've got flights, we've got exercise, we've got tips, taxis, iris, and penguins. So in order to load these datasets, we need to use the Seaborn function, load dataset, and then provide the name of the dataset in the form of the string. So when we do this, we'll see that the dataset is a data frame. And in the case of flights, we see we've got the series year, the series month, which is categorical, and the number of passengers. Let's now load the exercise dataset and have a look at it within the Variable Explorer. So here we see we've got the series ID, so each person in the study has an ID. They've also got a diet, and their pulse has been taken at various times during different types of exercise. Okay, and now we can have a look at the data types. And we see that diet, time and kind are category, and ID and pulse are int64. Let's now have a look at the dataset tips. So we see that tips is a data frame, and it's got the series total bill, tip, and size, which are all numeric. And then it's got the categorical series, sex, smoker, day, and time. And we can have a look at the data types of this data frame. And as I said, we've got total bill, tip, and size, which are all numeric, and sex, smoker, day, and time, which are all categories. We've also got the example dataset taxis, which is a bit more complicated. So it's got 2 time series, pick up and drop off time, and then it's got the numeric series, passengers, distance, fare, tip, tolls, and total, and then it's got some categorical series such as color, payment, pickup zone, and drop off zone. And under color, there's two different brands of taxi, essentially, the yellow taxis and the green taxis. And then there's two additional categorical series towards the far right called pickup borough and drop-off borough. And once again, we can have a look at the D types. So a lot of the D types are numeric, and all the categorical series are objects, which means at the moment they're all strings and haven't been explicitly converted to categorical series. Let's now have a look at the iris dataset. So we've got 4 numeric series which correspond to measurements taken at different parts of the plant. And then we've got the species of each of the plants that were measured. We've got a similar data set called penguins, which instead of measuring plants, measured some features of the penguins. So we've got the species, and we've also got the island that the penguins live on. And then because the penguins are mammals that have a sex, we've also got the additional series sex. So once again, the categorical series here are shown as objects, and they haven't been explicitly converted from strings to categories. Okay, so that's an overview of some of the inbuilt data sets, and we're going to have a look at these in a bit more detail using some of the data visualizations. So if we type in SNS dot, we'll notice that we've got some other modules. So we've got relational plotting functions, regression plotting functions, distribution plotting functions, categorical plotting functions, and matrix plotting functions. So if we have a look at our user profile and then go to our Anaconda free folder, lib, and then site packages, we can then select our Seaborn folder and we can see these additional modules here, as well as the palettes, which we've already had a look at. So if we type in sns.relational, we see 3 relational plots, such as the line plot, the scatter plot, and the relational plot. Now, we can call these plots from the relational module, or we can call them directly from the Seaborn library, which is more common. So let's have a look at the plotting function lineplot. So it has the keyword input argument data, and we must supply a data frame to this. And then it's got the keyword input arguments x and y, which we must assign to as series names within this data frame. So notice that when we plot this, we get a line plot, and x data and y data are shown. So the strings that we provide here, i.e. the names of the series, are automatically used as the x and y label. We've got a similar function called scatterplot, and this outputs a scatterplot, and the keyword input arguments are very similar. Notice that there's another keyword input argument called hue, and what hue can be assigned to is a categorical series. And notice now that what we've done is group together all the odd values and all the even values, and now each of these are plotted using a different color. And we can assign the keyword input argument palette to one of the names of the palettes that we've explored earlier. Let's now have a look at using a different data frame, the sign data we created before. So the data is going to be sign data, x is going to be the string x, y is going to be the string y, and let's set the hue to the string amplitude. So Seaborn's actually been pretty smart and realized that all our data is related, and as we increase the amplitude, it's basically applied a sequential color map for the amplitude. We can, however, override this and set it to the palette tab 10. And this uses the palette tab 10 and gives a similar plot to what we've seen before when we had a look at using matplotlib and using the color palettes. And this plotting function is a bit more sensible when we use a sequential color palette such as Magma or Viridius. So as this plot is based around matplotlib, we can use the axis method legend to change the position of the legend. Let's now have a look at the DataFrame flights and explore what's happening under the hood in a bit more detail. So what we're going to do is assign the data to the DataFrame flights, and then assign X to the series year, Y to the series passengers, and hue to month. So we get a new line for each month. And now what I'm going to do is assign this to the object name lineplot. And if we have a look in the variable explorer, we see that lineplot is of the type AxesSubplot and Ax is of the type AxesSubplot. And actually, if we type in lineplot and check whether it's equal to Axis, we get the result true. So what this essentially has done is it's taken the currently selected matplotlib axis and it's just modified it directly. So if we have a look at the attribute lines, we see that this is a list of 24 lines. So what the Seaborn function has done is it's updated the currently existing matplotlib axis and added 24 lines to it. And we can use the axis methods getXLabel and getYLabel to get the X and Y label respectively. Now let's create subplots with 2 rows and 1 column. So notice that when we use this function, we plot to the bottom subplot because this is the currently selected axis. So because the Seaborn plotting functions are separate from matplotlib, they can't be called directly from an axis. So what we need to use is the pyplot function setCurrentAxis, and then we set our current axis, and then we call the Seaborn plotting function, and this plots in the desired axis. So for example, we can create a line plot in the top subplot, and then we can create a scatter plot in the bottom subplot. So Seaborn has plotting functions which act on the axis level, and it's got plotting functions which act on the figure level. So in order to demonstrate this, we're going to have a look at the relplot, which is the relational plot. And this acts on the figure level. So we'll notice that it's got a lot more keyword input arguments than the line plot and scatter plot that we used before. So what I'm going to do is create a new figure and axis, and then I'm going to create a line plot. And then I'm going to create a new figure and axis, and then I'm going to create a relational plot. And I'm essentially going to input the same keyword input arguments. However, I'm going to add the keyword input argument kind and assign it to scatter. So notice that figure 1 turns out as expected, but figure 2 is blank. And then we've got figure 3. So the reason for this is that this plotting function acts on the figure level. So what it essentially does is it creates its own figure and everything is plotted within its own figure. So any figure created before is simply ignored, and you've moved on to a new figure, selected this new figure, and selected the axis in this new figure. So if we have a look at the Variable Explorer, we see that this is a FacetGrid, which means it's basically a figure level object, i.e. a figure with a grid in it, and the grid can hold one or multiple subplots. So if we have a look at some of these other keyword input arguments, we see we've got row, column, and column wrap. So if we run this script and assign month to column instead of year, we see that we've got 12 subplots, one corresponding to each month. And because we use column, they're all shown in an individual column. And we can use the keyword input argument with column, call wrap, to specify the maximum number of columns we want. So let's assign this to 4. And after we get to 4 columns, we move on to a row. So this gives us the same 12 plots that we've seen before. We can also use row, and this gives us 12 different rows instead. And the relational plot is kind of generic between the line plot and the scatterplot. So we can toggle the kind from scatter to line to get a line plot instead. So if we change hue back to month and compare the line plot and the relational plot with the kind equals line, we see that they're very similar, except the sizing of the relational plot is slightly different. And for the line plot, we've got the figure and the axis, and we can access the figure attributes and methods, and we can access the axis attributes and methods. Now, in the case of relplot, if we have a look at this, this is of the type FacetGrid, and the FacetGrid has the attributes figure, axis, and ax. So we can assign the attribute figure to a new object named fig2, and we can assign the attribute axis to a new object named ax2. So fig2 is of the type figure as expected, but ax2 is an array of AxesSubplots, and in this case, because we've only got one AxesSubplot, it's a 1x1 array. For a FacetGrid with a single AxesSubplot, we can also use the attribute ax, which will give us this single AxesSubplot. Let's now have a look at the regression module. So we see we've got this regressional plot, and then we've got the residual plot. So let's have a look at this regression plot. And once again, we typically call this from the Seaborn library directly. And let's have a look at our DataFrame lin data. So here we're going to use the keyword input argument data and assign it to lin data. And so X is going to be the series X data, Y is going to be the series Y data. And I'm going to leave all the other keyword input arguments as their default. So what this has done is it's fitted a linear regression line to this data. So the data is shown as scatter plot, and the linear regression line is drawn through this. So let's change the subplots to have 2 rows and 1 column, and then we're going to set the current axis to axis 0, create this plot, and then beside it we're going to create a residual plot. And we'll use the same keyword input arguments in both. So here we see the data points shown as a scatter and then a regression line drawn in the middle. The residuals are the difference between the data point and this line. And for a good fit, these should be around 0. So in this case, you can see it's a pretty good fit. And most of the data points are quite near to 0. And this is expected because we created this data from linear spaced x and y values, and the y values just had some additional noise added. We can change the order, so we can change it from the default order of 1 to an order of 2. And this will fit a quadratic equation opposed to a straight line. And you can have a look at the start of this line to see that there's a bit of a quadratic effect, although it's not very strong. And it's not very strong because this data is linear data. Okay, so one thing that gets commonly asked is, can the user plaster the equation that the regression line displays on the plot? And the developers of Seaborn have been quite against this. And the reason that they're against this is because a lot of people use plotting functions and then add an equation to it and then don't really understand the equation and then quote it in a report. So if you want this functionality, you're going to have to calculate it using the polynomial class in the polynomial module within numpy. So we need to use the Polynomial Fit method to create a new instance of the polynomial class. And to do this, we need to supply the x data, the y data, and the degree of the polynomial. And then we need to use the polynomial function convert to convert the polynomial and cast it to a string. Now, unfortunately, there's no means of rounding here, so the string is just massive, specified to a very large number of decimal places. And if we have a look at these two equations, we see that the AxisGrid term has a very small coefficient for the second polynomial, and therefore it's pretty much indicating that it fits pretty well to a straight line and the additional term is not needed. So I'm going to use the figure method supertitle, and I'm going to assign a supertitle to this equation. So let's do this for the linear fit. And then we can go ahead and create another plot which does this for the quadratic fit. So if you've got a bit more time, you can manipulate the string so it doesn't have this obscene number of decimal places. Hopefully they should make this easier in the future using the convert function of the polynomial, i.e. add a keyword input argument to specify the number of decimal places. Let's now have a look at the linear model plot, lmplot. And once again, we see that this is a FacetGrid on the figure level. So you can see this because it's got the keyword input arguments call row and call wrap, which will create additional subplots. Okay, so if we have a look at this within the variable explorer, we see that this is a FacetGrid. And for this, we can set the column to be even and odd, so this splits the odd and even data. Or we could use the row instead. So this gives us 2 rows instead of 2 columns. Let's now have a look at the flights data. So we're going to set X to the year, Y to the passengers, and column to the month. And once again, we can wrap the columns to 4 columns. Let's move over to the taxis data frame now, which is a bit more complicated. So we're going to set X to distance, Y to fare, and the hue to color. Okay, so the color doesn't actually match with the color here, so it's using the default palette. Let's create a yellow-green palette, which corresponds to the colors yellow and green, respectively. So the number of colors here is going to be 2. And we can assign this palette to the yellow-green palette. Okay, so we've got a lot of additional series that we can split this along using a FacetGrid. Let's take the number of passengers, for example, and set this to the column. So here you can see the differences in the fares and the distance for the 2 taxis. So for 2 passengers, the yellow taxi is going to be slightly cheaper. For 3 passengers, the green taxi looks to be slightly cheaper. Once again, we can use the column wrap and assign it, in this case, to 3. And so we've got 3 columns, and then we move on to the next row. So let's get the figure and the axis from this lmplot and assign it to Fig and Axis respectively. So if we have a look at Fig, it displays the figure in the console. If we have a look at Ax, it displays the axis. So here we can see what axes have an X and Y label, and we can also see the title of each axis subplot. So in this case, the Y labels are only shown on the left subplots, and the X label is only shown on the bottom subplots. So what we can actually do is get the Y label and set it to whatever we want it to be. So for example, let's just set it to hello. And if we just add these lines of code into our script, we now see that the Y label in this first axis subplot says hello. So here you can see how you can use the axis subplot attributes figure and axis to manipulate the figure and axis respectively. So this gives you the matplotlib functionality to manipulate the FacetGrid. Okay, so now let's have a look at the distributions module. And from this we can see that there are a number of distribution plotting functions, such as the rugplot, the histplot, the kdeplot, the ecdfplot, and the displot. So in order to have a look at these, what we're going to do is import numpy random as random, set the random seed to 0, and I'm also going to import the scipy stats as stats, and I'm going to create a data frame called random data, and this is going to have 10 random normalized data points. So we can view this data frame in the variable explorer, and it's just got 10 values which we can conceptualize pretty easily. So let's create a new figure and axis, and we're going to have a look at a rugplot first. So a rugplot just essentially has a single x-axis and a straight line is drawn where each data point is found. So the height is completely arbitrary, and each data point has the same height. So here you can see that this data point is this one is this one, and so on. Let's now have a look at a histplot. So a histplot basically groups these lines together into bins. So this single data point's on its own, this single data point's on its own. These two are grouped together in a bin. These four are grouped together in a bin. And then these two are grouped together in a bin. So you can see the analogy between the rugplot and the histplot. Now let's have a look at the kdeplot. So this gives a distribution of the data, and this distribution is related to the rugplot. So let's have a look to see how they're related. So I'm going to create a figure with 3 AxesSubplots, and there's going to be 3 rows and 1 column. So at the top, we're going to create our rugplot using pretty much the same code as above. So next we're going to set the X limit. And then because the rugplot is a line collection, it's found on the collections attribute of the AxesSubplot at index 0. And what we are wanting to do is just change the colors to be a different color in the default Seaborn color palette. So each line is a different color. Now we're going to have a look at the middle AxesSubplot. And so we're going to take the value from random data as being our central value. And then we're going to calculate the variance of this. And then we're going to calculate sigma by taking the square root of the variance. And then we're going to plot a Gaussian from a start value of mu minus 3 sigma to a stop value of mu plus 3 sigma and take 100 data points. So basically we're going to plot a Gaussian at each of the lines on the rugplot. And once again, we're going to set this X limit. So basically what the KDE does is it takes each of the lines in a rugplot and plots a Gaussian. And then it combines all the Gaussians together and creates this KDE plot. So if I go ahead and just create a plot of this KDE plot in the last AxesSubplot, we can clearly see how the rugplot and the KDE are related. Okay, so let's now have a look at the rugplot, the histplot, and the KDE plot all together side by side. And let's return all the colors to just being red. So I no longer need this line where I use set properties to change the color of each line in the line collection. Okay, so we've got a small number of data points. Let's up this now to 1000. And there's too many data points in the rugplot to see clearly, so I'm going to lower the alpha. And this kind of gives us a visualization of how dense the lines are. And as we increase the number of data points, the histogram and the KDE begin to strongly resemble one another. Okay, let's just simplify our code a bit. Instead of assigning each of these plots to an AxesSubplot, this is not needed because they will automatically update the currently selected AxesSubplot, and so we can just use this directly. And it cleans up the code quite a bit. giving the exact same plot. So let's now have a look at an empirical curve distribution function. And once again, we're going to compare it to the rugplot. So if we have a look at this, what we've got is 1 point out of 10, which is 0.1 proportion. We move along till we get to next data point, and now we've got 2 points out of 10. And we basically move along as a step until we get to 1.0, which means we've got 100% of the points covered as we move along from left to right. And as we increase the number of data points, we can see that this smooths out. And so the proportion at 0 is 0.5, which means half the values are negative and half of the values are positive, as expected for the random normal distribution. Let's now compare the random normal distribution to the random distribution. So we're going to create 4 AxesSubplots. And in the top AxesSubplot, we're going to add 2 rugplots, one of the random normal and one of the random distribution. So let's see this works as expected. So we see the random normal distribution is centered around 0, whereas the random distribution is between 0 and 1. Let's now create a histplot of both of these. So we'll use an automatic number of bins. Actually, we'll change the number of bins to 50. And here we can see the difference between the random normal and random distribution. Now they're both the same color. So let me just lower the alpha of the random normal so we can see it a bit more clearly. Okay, we want this to be the same color as the rugplot of the random distribution. So if we have a look at the color palette function, we know that the 0th color is the blue and the first color is the orange. So let's assign this to the orange color. And then we don't need to be as restrictive for the alpha value for the random normal distribution. Okay, so let's now create a KDE plot for both these distributions. And here we can see the KDE of both distributions. And we can see that this looks very similar to the bar graph as expected. So let's now have a look at the empirical curve distribution function for each of these distributions. And we can see this looks exactly as expected. So for the random data, it's 0 proportion at 0. And then it's a straight line until you get to 1 where you've reached 100% of the data values. So all of the distribution plotting functions we've previously used have been on the axis level. So similar to the other modules that we've seen before, we've got an equivalent plotting function, which is the displot, which can be used to create a distribution plot that's in the form of a FacetGrid, i.e. on the figure level. And this has the keyword input argument kind, which can be used to switch the different kind of plot. So by default, it's a histogram, and we can change it to a KDE or a ecdf. So once again, in the case of Seaborn, it's a good idea to learn what the axis level plots do and learn about our keyword input arguments, and this makes it much easier to use the figure level plot. Okay, so let's now have a look at the penguins example dataset. So we've got multiple numeric series and multiple categorical series. So let's set the data to penguins, X to bill length millimeter, the kind to hist, the hue to species, and the column to sex. And if we look at the species, it's easier to distinguish the blue species from the green and orange, which overlap. Now we have 4 numeric series, so what happens if we switch X from bill length to bill depth? And now you notice that it's easier to distinguish the green category from the blue and the orange category, which overlap. So is there a way of combining the 2 plots together? Well, if we go back to the distribution plot, we'll notice that we have the keyword input arguments X, and we also have the keyword input argument Y. So we can set X to the bill length in millimeter, and we can set Y to the bill depth in millimeter. So when we do so, instead of having a 1D bar graph, we're going to have a 2D bar graph. So let's run this, and here you'll see that instead of having a bar, each point is represented as a square. And shading is used to indicate the density of the data points. And in this example, the 3 species are quite widely separated, so you can easily distinguish the blue blob, the orange blob, and the green blob from one another. And if we change the kind from hist to KDE, we instead get a contour style plot. And once again, we can see that the 3 species are easily distinguished using these 2 features. So sometimes we want to see the 2D and 1D representation beside each other, and we can do this using a joint plot, which is found under the AxesGrid module. And this creates an instance of the joint grid class, which again operates on the figure level because it has multiple AxesSubplots. So if we use identical keyword input arguments for the data, but remove the FacetGrid options such as the column, and remove kind using the default, then we get this joint plot, which is an instance of the AxesGrid class. So by default, the middle axis has the kind scatter, and the left and right axis have the kind KDE. So if we have a look at joint plot, we can access a number of methods and attributes available for an AxesGrid class. And you'll see that we can access the figure and the 3 separate axes. So we've got the margin x-axis, the margin y-axis, and then we've got the joint axis. And you'll notice what axis is what when you have a look at these attributes and see the x label and y label. And once again, we can change the kind from the default value to histogram or to KDE. So let me just add the keyword input argument and set it to hist. And this is what it looks like as a hist, and this is what it looks like as a KDE. So in the distribution plots that we've just currently used, we've only been able to assign 2 of the numeric series to x and y respectively. And we just picked the first 2 to see what these look like. So these may not necessarily be the best 2, and in terms of the best 2, you want the 2 that most clearly distinguish the 3 different species. So what we can do is actually create a pair plot. So this will give a separate AxesSubplot for each XY pair available, and along the diagonal it will show just one of them the features. So in this case, by default, it's using a scatter for the XY pairs, and it's using a KDE for the single feature along the diagonal. So you'll see in some of the AxesSubplots that it's very easy to distinguish the three different categories. However, in some of the other AxesSubplots, two of the categories essentially overlap, making them indistinguishable from one another. So as you've seen, we've got a different kind along the diagonal as we do along the rest of the AxesSubplots. And we've got the keyword input argument kind and diagonal kind, and we can change these both to hist, which gives a plot like the following. We can also change them both to KDE, and we can use a mixture of both of these if we want as well. And we can also change the kind back to the default, which was scatter. So by default, we plot x versus y and y versus x for each pair of numeric features. And these essentially give the same information. It's just the different features are on the different axes, but the ability to separate the three categories will be the same. So we can set the corner to be true to only get one of these sets of plots, which can be a bit easier to read. Seaborn also has a number of categorical plots found under the categorical series. So let's just have a quick look at these. So we've got the box plot, and this works on the axis level. So let's use the exercise data and set x to be the pulse, and this gives a horizontal box plot. If instead we set y to be the pulse, we get a vertical box plot. And if we set x to the category kind, then we're going to get a box plot for rest, walking, and running, i.e. the three different categories in kind. And unsurprisingly, the pulse rate increases as the level of exercise increases. We can also set hue to be another categorical series, such as the diet. And in this case, the diet is low fat or no fat. So we can assign this to hue, and we can also assign a hue order. And we can assign our own custom palette here. And from this, we can see that there appears to be a difference between the two different diets, with the low-fat diet having a lower pulse than the no-fat diet. So we can change to another categorical plot, such as a violin plot. So for some reason, the legend isn't in an optimal position, so let's just move this to the upper left. And the violin plot shows the KDE. And because we've got a hue that has two values, we can split this, and it's going to show the low-fat diet on the left and the no-fat diet on the right. So we also have the strip plot, which is essentially a scatter plot of both of the two data series. And we've got a very closely related plot called the swarm plot. So the swarm plot is supposed to minimize the overlapping of data points between these two different species. Sometimes it's not possible to do this, so we also need to use the dodge parameter. And this will offset the swarm of data points for one category with respect to the swarm of data points of the other category. So this categorical data can also be presented using a bar graph, or even just a single point. And as we've seen, all these plots operate on the axis subplot level and use X and Y. We also have a count plot, which is similar to a histogram plot, except it's going to count discrete values, i.e. and not group them together in a bar. So for this, we can only specify an X parameter because the Y is going to be the number of counts. And like the other plot types that we've seen, we've also got the figure level FacetGrid cat plot, which groups these all together. And you can switch between these using the keyword input argument kind. So the cat plot is going to be a facet grid, and by default it uses a swarm plot. So we can change this to violin, for example. And when we do change it to violin, we can use the additional keyword input arguments for the violin plot. And because it is a facet grid, we've got column, column wrap, and row. And in this example, we can assign column to time, and we'll get a subplot of time, which is 1 minute, time, which is 15 minutes, and time, which is 30 minutes. And you see the last subplot shows the highest apparent difference between the two different diet plans. Seaborn also has a matrix module, which contains a number of plotting functions used for matrices. Now, these matrices should be in the form of a data frame. So if we have a look at the flights data frame, we see we've got the data as series X, Y, and Z. So X is the year, Y is the month, and passengers are the Z values. So we can use the pandas function pivot to assign the data to flights, the index to month, the column to year, and the values to the number of passengers. And now the data is in matrix form, and we can view this in the variable explorer to see what it looks like. And we can use the Seaborn plotting function, heat map, to visualize this. So this is similar to the matplotlib plotting function, pcolor. And we just need to supply our data as a pandas data frame in the matrix format. We have a number of optional keyword input arguments, such as vmin and vmax. And we can also assign the color map. So for example, let's change it from the default, which is magma, to viridius. We can also change it to the black and white bone. We can also add line widths to each square just to separate them out visually. And we can also annotate these. So let's just assign annotation to true. And it's annotated each of these squares in scientific notation, which doesn't really make sense for these decimal values. So we can change the format specification to decimal. And it's just going to give us the decimal values. And for this data set, it's basically displaying the same pattern that you see within the variable explorer. And we can create our own color palette for this. So let's create a blend palette using the colors sky blue and hot pink. And let's have 30 colors. So let's just assign this to a variable called blue pink. And then set the CMap input argument to blue pink. And this comes out pretty well, and it's basically the opposite of what you see within the variable explorer using similar colors. So one thing I just want to clarify is that created an AxesSubplot. So operates on the axis level. And we have the figure level cluster map, which is essentially a heat map that gets clustered together. So if we have a look at this, we see that the winter months are clustered together because there are a lower number of flights, and summer months are also clustered together because there are a higher number of flights. The years are shown roughly in order because the number of flights increases as the year increases, although some of the years have been swapped. And this operates on the figure level, and we can change the color map. So I think this is a good point to end this video, and I've covered the Seaborn syntax in quite some detail. Now, Seaborn do have an example gallery, and there's a lot of plot types that I've not covered in this video. However, you now understand how Seaborn works, and it should be pretty straightforward to have a look at these example plot types and then apply them to your own data sets.